People are starting to join the seminar now. I'll just give another minute or two to let people join, and then we'll go ahead and get started. Okay, so it's 1 o'clock now. I'm sure we'll get a few more people joining in, but we only have an hour here, and we want to maximize the time of our excellent speakers this week. So my name is Dan Lipson. I'm a research soil scientist at the Soil Health Institute, and I'm one of the co-organizers of this seminar series. And this is our 5th one in the series, focusing on cover crops. And so without further ado, I want to introduce our first speaker, Shelby McClelland, and she's going to be talking about when is cover cropping an effective practice to increase soil carbon. Oh, and just one more thing, as you're listening, you have the questions you submitted in your registration already, but if you have other questions that come up, you can just post them in the question period. Shelby will talk for about 20 minutes, and then we'll have plenty of time for questions. So please put any questions you have in there. So take it away, Shelby.
Great, thank you, Dan. Let's see here. I'm gonna go ahead and hide some of these things so I can, there we go, perfect. Great, so thank you again, Dan, for that introduction. And I'm really grateful for the opportunity to present during this webinar series today. I look forward to contributing to the conversation about building soil carbon under cover crops by synthesizing the recent literature, sharing some work by myself and colleagues on this topic, and offering some clarity about how the scientific community can continue to support producers and decision makers on when and where to implement this practice. So one of the key opportunities to increase carbon drawdown to combat the climate crisis is through changing agricultural management practices of soils. Cover crops are one such practice. These are crops that are not harvested, and their residues are allowed to decompose in the field. Typically, cover crops are grown during the traditional fallow periods between cash crops, so increasing the time a field is cropped, or in the case of orchard and vineyard systems, in the rows between trees and vines, taking advantage of space either kept fallow or not intentionally managed. Cover crops effectively represent an intensification of the agroecosystem and provide additional opportunities for plants to capture and return atmospheric carbon to the soil. Increasing the quantity of plant biomass returns and the quality of this biomass, together with favorable soil conditions for incorporation into soil organic matter, is what ultimately leads to increases in soil carbon stocks. But in reality, we all know that it's not quite so straightforward. Our agroecosystems are diverse and require different management strategies to not only achieve high yields, but also to maintain soil health and profitability for producers. And of course, producers face numerous environmental challenges, depending on where they are located and how they farm, including water limitation, weather variability, soil quality issues, and challenges in planting and harvesting. Understanding this variation is key to increasing public and private sector confidence in cover cropping to deliver carbon sequestration benefits. There is a growing body of scientific evidence supporting the wider implementation of cover crops in agroecosystems. However, to improve adoption and recommendations for implementation, we need to know why agroecosystem responses to cover cropping varies, and in what ways management contributes to this variation. Today, I hope to continue to shed light on what management contexts are best suited for cover cropping, where cover cropping can and should be applied, and how models and decision support tools can support producers and decision makers with scaling cover crop adoption. First, I'll begin by reviewing several recent global analyses that quantify the expected soil organic carbon stock change under cover crops. I'll then share some recent work conducted with colleagues at Colorado State University about how cover crop management decisions and environmental variables affect the magnitude of soil organic carbon stock response. I will also provide some examples of how this knowledge can contribute to decision support tools and towards efforts to better quantify how improved soil management can contribute to net zero emissions goals. So one of the earlier meta-analyses on soil carbon responses to cover crops was completed by McDaniel and colleagues. And while they did not quantify soil carbon stock changes, their analysis showed that relative to cropping systems with no cover crops tended to lead to an increase in total soil carbon of nearly 10%. And following the McDaniel publication, Poplow and Dawn demonstrated through their global analysis of 30 studies and 37 different sites that cover crops increase soil carbon stocks with an annual change rate of about 0.32 megagrams of carbon per hectare per year. In turn, building on this work, Abdallah and colleagues showed through another recent analysis the net climate benefits derived from cover cropping by considering not only soil carbon stock changes, but also soil nitrous oxide emissions and nitrogen leaching. The overall effect of cover crops resulted in an annual soil carbon sequestration rate of more than 0.5 megagrams of carbon per hectare per year from 47 observations. And recent work by Gian and colleagues using the Research Landscape tool from the Soil Health Institute showed similar global rates of carbon sequestration under cover crops of about 0.56 megagrams of carbon per hectare per year. So with the growing attention on soil carbon markets in the United States and in Europe, there's a need to better quantify the expected soil carbon stock changes under cover cropping from temperate climates and representative cropping systems. There's also growing interest in understanding how decisions made at the field scale, such as the selection of a grass versus a legume cover crop, the number of cover crop species planted, the type of termination method, or even the broader cropping system contributes to soil carbon stock change. So among the few recent analyses on soil carbon responses to cover crops, most were unable to demonstrate a difference from soil carbon or in soil carbon response due to cropping system management, climate, or soil mineralogy. So for example, Poplow and Dawn did not find a difference between cover cropping systems that practice no-till relative to tillage, or find differences between legume and non-legume cover crops. Gian and colleagues, on the other hand, did find a difference in carbon stock response between single species and mixed species cover crops, but there were no differences by overall cropping system type. So as part of my dissertation research with colleagues at Colorado State University, we conducted a meta-analysis to estimate cover crop effects on soil organic carbon stocks as measured from 0 to 30 centimeters in temperate climates. We estimated the relative importance of different cover crop management decisions and their interactions on soil organic carbon response. And finally, we also worked to identify important environmental controls on soil organic carbon response under cover crops. So in our work, we hypothesized that the response of soil organic carbon to cover crops is most likely influenced by producer management choices, such as when the cover crop is planted and when it is terminated, the type of cover crop that's planted, as well as the diversity of that mixture. So whether it's planted as a single species or if there's more than one species present. We also hypothesized that the termination method of that cover crop, as well as overall system tillage, likely played a role in soil carbon response. And finally, even more broadly, that cropping system rotation likely had an impact. However, we also expected that the magnitude of this response was likely influenced by differences in soil mineralogy, as well as climate. So our final data set included 40 publications and 181 observations, indicating that some publications we included had more than one cover crop treatment. So to be included in our data set, publications needed to be field-based. They needed to use the term cover crop, green manure, or catch crop, but regardless of the term used, that residue could not have been harvested. It needed to be allowed to decompose in the field. The study had to occur in a temperate climate, which we delineated really at the country scale. The treatment with the cover crop, as well as the control, needed to exhibit similar management. So basically the differences that we were looking at, we could really ensure that they were coming from the inclusion of a cover crop or not. And finally, we needed enough data to actually be able to quantify carbon stock response. So meaning we needed to be able to have bulk density estimates to actually be able to quantify stock and not just leave it on a concentration basis. Another key difference in our meta-analysis was accounting for the effects of non-independence. We also applied an imputation method to account for missing standard deviations in some of these studies, so that way we could conduct a weighted meta-analysis. And we also only used the final pairwise comparison between a treatment and a control site in our analysis. So across all studies in our analysis, cover crops increased soil organic carbon stocks by 12% when measured from 0 to 30 centimeters for an approximate annual change rate of 0.21 megagrams of carbon per hectare per year. So to briefly orient you to the way this graph is laid out, as it'll be similar to several other slides that I plan to show, on the x-axis is a log response ratio. Basically, the only thing you need to really be looking at here is looking at the solid black line at 0. Anything that is to the right of that solid black line indicates that the cover crop treatment led to an increase in soil organic carbon stocks. And anything to the left of that line means that actually the cover crop treatment led to a decrease in soil organic carbon stocks. So going back to this annual change rate estimate, you might notice that it's a bit more conservative than previous publications. But again, our study had several noticeable differences from past syntheses, including the number of publications we included, the statistical methodology we applied, as well as our concentration on temperate climates. Also, again, this is the average response without considering the role of management or environment. And the results of our statistical test indicated that the variation that you can see here was likely driven by some other factors, which led us to examine different management and environmental factors more closely. So the most important management factor we identified was when the cover crop was planted. We found that cover crops planted as continuous cover and cover crops planted in the autumn but terminated by winter kill resulted in about 20 to 30% higher soil organic carbon stocks than cover crops that were allowed to overwinter or that were planted in the summer. The second most important management factor was the cover crop yield, or the amount of biomass that was produced by the cover crop. And our analyses indicated that maximizing for above ground plant production increased soil organic carbon 20% more than the lower biomass production categories. And while not shown here, we also observed differences in soil carbon responses between no-till and conventional till production systems and cropping rotation, where perennial systems had 20% or higher soil carbon stocks relative to annual cropping systems. So of the environmental drivers, we observed that cover crops grown in warmer and wetter climates increased soil organic carbon stocks more than cover crops grown in drier and cooler climates. And we also observed, again not shown here, that soils with more than 20% clay content had higher soil organic carbon stocks under cover crops than soils that were predominantly sand, which is consistent with other recent work. And some other interesting things that we observed that again are not shown here is that we found important interactions between the type of cover crop diversity and growing window, which I'd be happy to talk about more later. So to kind of synthesize and bring all this information together, we found that across a variety of management systems and climate and soil conditions, that cover crops increase soil carbon. But the size of this increase really depended on when the cover crop was planted, how well it established and yielded, and other on-farm management decisions like cropping system rotation and tillage. We also found that environment does play a role. Higher clay content soils showed higher soil organic carbon stocks. and subhuman climates, especially those located in the southeastern United States, showed greater soil organic carbon stocks compared to drier and cooler climates. So what I think is quite interesting about these management factors in particular is that they really adhere closely to the principles of soil health, increasing living roots, increasing diversity, increasing soil cover, and minimizing disturbance. So despite this important step forward regarding the impact of management decisions on soil carbon responses, there are still important questions remaining about when and where cover cropping is a viable practice from a wider agroecosystem productivity and climate change perspective. So for instance, there are still relatively few empirical observations from tropical climates relative to temperate climates, as you can see here. Second, soil sampling below 30 centimeters still remains relatively rare. And work from California indicates that the soil carbon benefits of cover cropping could be overestimated in some systems if we only account for the topsoil carbon responses. And I would also add that many of the data reported in the literature only allows analysis by fixed depth rather than equivalent soil mass. There are also additional cover crop management strategies that merit closer evaluation that we couldn't include in our analysis. A recent work by colleagues at CSU showed that grazing cover crops can maintain the soil health benefits provided by ungrazed cover crops in dryland systems. And in some management contexts, grazing cover crops could increase their profitability for producers and help to offset the short-term yield impacts of cover crop moisture use in water-limited environments. Finally, any management practice that's implemented to mitigate climate change must consider the net greenhouse gas impact. So in many cases, increases in soil carbon stocks can lead to increased soil nitrous oxide emissions, negating some or perhaps all of the climate benefits that are gained from changes in soil carbon. So earlier work by Beish et al. Indicated that cover crops do not always decrease soil nitrous oxide emissions, and that the choice of cover crop type, such as whether it's a legume or a non-legume, as well as how those residues are managed, so whether they are tilled into the soil or left to decompose on the surface, can all impact the magnitude of soil nitrous oxide emissions responses. And so there's still a lot of uncertainty regarding the trade-offs that may occur with nitrous oxide emissions, and this can be best addressed by collecting more long-term data at greater spatiotemporal resolutions. So in the interim, soil biogeochemical models and decision support tools can begin to assist us with understanding the net climate benefits derived from cover cropping. And they can also help us understand the magnitude of emissions reductions at different scales and under different future adoption scenarios. So following our meta-analysis, we took many of these same studies and used them to improve two decision support tools. The first, the Comet Farm tool, which is supported by the Decent biogeochemical model, and the other was the Cool Farm tool, which is an empirical model that uses IPCC Tier 2 approaches to estimate greenhouse gas emissions. Our work with the Cool Farm tool is led by Helen Hughes and John Hillier at the University of Edinburgh, and this is still ongoing. So today I'm just going to focus on the results from our recent efforts to parameterize and validate Decent for cover crop production. So our model validation work found good agreement between empirical and modeled estimates of soil carbon change, but poor agreement with soil nitrous oxide emissions. Soil organic carbon difference between cover crop and control treatments was 178 grams of organic carbon per meter square, indicating that cover crops on average led to an increase in soil organic carbon. And the model was able to represent this increase in soil organic carbon under cover crops, explaining 36% of the variation in the observed results. And actually, when we went to account for the number of years under cover cropping in the experiment, the model was actually able to explain 67% of the variation in soil carbon response. As you can see in this rightmost graph here, the observed differences in soil nitrous oxide emissions were highly variable across the sites. And the model was really unable to describe this observed variation, and there was some evidence of systematic bias. Part of this poor agreement likely stems from differences in empirical data reporting and the time step that the model uses to actually estimate nitrous oxide emissions. However, the model did tend to capture the general tendency of cover crops to lead to lower annual soil nitrous oxide emissions relative to a non-cover crop control. So model validation exercises are quite important for helping to reduce uncertainty in emissions reduction potential and for increasing the confidence in decision support tools used by instructors, land managers, policymakers, and other stakeholders. So DACENT is the underlying soil biogeochemical model for several decision support tools that are operated at different scales. It supports the Comet Farm tool, which is a whole farm greenhouse gas accounting tool, Comet Planner, which can evaluate the potential for carbon sequestration and greenhouse gas reductions from adopting cover crops and other conservation agricultural practices at the county level. And also the Carbon Reduction Potential Evaluation Tool, or CARPE, which was developed by American Farmland Trust and USDA ARS to evaluate improved agricultural management practice adoption at sub-state, state, and the national level. Modeling can also assist us with quantifying the theoretical maximum net climate benefits from cover cropping, but also the net climate benefits under current cover crop practice adoption trajectories. So recent work by Kimata and colleagues with DACENT showed that across the European Union, changing crop sequencing could limit soil nitrous oxide emissions trade-offs under cover cropping and help to reduce, reduce these over longer time horizons. And for the United States, our work with CARPE demonstrates that there are significant net climate benefits that can be achieved with increasing the nationwide adoption of cover crops. So 2017 adoption levels of cover crops provided about 5 million tons of carbon dioxide equivalent reduction potential benefits. And so under two different adoption scenarios, the first being a business as usual adoption scenario, where we just applied the linear increase over time that we've been observing in cover crops. This reduction potential almost doubles when we look at this over the next 10 years. But under a different adoption scenario where we actually work to accelerate adoption timelines over the next 10 years, this potential increases to 25 million tons of carbon dioxide equivalent per year. So through my presentation today, I hope I've provided some additional insights into when and where we can expect soil carbon benefits from cover cropping, and how decision support tools can continue to help us quantify the carbon sequestration and net climate benefits of cover cropping at a variety of scales and under different management and adoption scenarios. Management decisions made by producers can impact soil carbon responses to cover crops. Our meta-analysis demonstrated that decisions like when the cover crop is planted and terminated, and even the number and types of cover crops planted within these growing windows can increase the magnitude of soil carbon stock change. However, the net climate benefits are still uncertain. The soil nitrous oxide response to cover crops is not well understood, making it difficult to capture these dynamics in soil biogeochemical models that underlie decision support tools. So more empirical research across different climates and under emerging cover crop management opportunities such as grazing, as well as better quantification of whole soil profile carbon stock changes and year-long soil nitrous oxide responses can help us address some of these gaps to reduce model uncertainty. Better empirical data sets and data reporting together with model improvements can increase confidence in the wider adoption of cover crops and help move the agriculture sector forward towards realizing its contributions as a natural climate solution. So thank you all again for your attention today, and I look forward to addressing any questions you may have.
Well, thank you so much, Shelby. That was a lot of information. So we got quite a few questions. And one of the ones that comes up a lot, you touched on kind of all of these, whether it's mineralogy or climate or cropping system. And, my bias as someone who lives in Colorado is one question you hear a lot is, what about arid regions? Mm-hmm. And so in the work that you presented today, is cover cropping viable in arid regions?
That is a really great question, Danny. Yeah, and having come from Colorado State, definitely something that's on my mind, and a lot of colleagues of mine are working on this very question. So in our actual data set, I'm trying to remember, I think we had one site from Colorado and a couple also from the Great Plains that are classified as being more arid. And so I'm trying to recall specifically whether those led to increases or not. But I think that there is some evidence that they can lead to increases in carbon over time. It just may take longer than especially what we have currently in the literature. So I will point out that most of the studies that were included in the meta-analysis probably only had cover crops for about 3 years or so, which is quite short as we know, and it takes a bit longer than that to really see sustained changes in soil carbon. And so I think there's still a lot of question, right, in these more arid regions, whether we can actually achieve these same gains. And I think we could say no, that we won't quite see the same gain in soil carbon as we would from maybe somewhere that's more humid, like somewhere in the southeastern United States. But there's more reasons than just carbon, right, that we might be implementing cover crops in these systems.
Great, thank you for that. Another question that came up is at least some of the studies in your work, you presented kind of annual rates of change, and you mentioned several of these studies are, relatively short. Some of them are much longer. But is there kind of a saturation potential, or how long would you expect cover cropping to, show those rates that you presented?
Exactly. Yeah, I believe I have to remember from the Poplow and Dawn study. I think they did some work to actually look at the carbon saturation point. And I know the Kimata study as well that used DACENT to actually model using the Lucas soil data set to actually model out through 2100, both the soil carbon and the greenhouse gas emissions dynamics. But what I recall from that study is I think they found carbon saturation around 2040. And I don't remember the exact year they started their analysis, but my guess is that was about 20 years or so. They started seeing, and then once the soil was saturated with carbon, there was no more changes in carbon. That's when they started seeing these trade-offs with nitrous oxide emissions because of the buildup of nitrogen. So I think we definitely, this won't continue into perpetuity, right? We know that there's going to be some leveling off, and so as we kind of show with this CARPE work, the sooner we can get start building up carbon in soils, the better off we'll be for meeting a lot of our climate goals here.
One of the other things that you mentioned is the depth issue, and even more so, in tillage, we talked about it in the last seminar, these depth issues, and you mentioned study from California where they, found differences at depth, and so we certainly need more data. Do you have any thoughts on what the mechanism might be for why cover crops would lead to differences at depth?
Yeah, I'm trying to remember from that Tautja study, which was quite a good study, and if I recall too, I think it was a rather long-term study as well, where they had, not just cover cropping. I think they also had what they labeled as an organic system, so that was including amendments and cover crops. And they also looked at different cropping system types as well, and I don't quite recall what those were, but in one of the cropping systems, they looked at, yes, they did find these losses in soil carbon at depth, and they really emphasized that if they had only looked, I think at the top 30 centimeters, they would have had much different conclusions if they had actually gone down the whole soil profile. And so why they didn't actually measure roots to that depth, I believe, that was one of their main hypotheses, was that there was some priming that was happening through the cover crops they were planting and the system, that actually there was that was kind of the mechanism responsible for why we were seeing carbon loss at depth. So.
Okay, well, that's a good lead into the next question, because there were, a couple people who asked in some way about the role of microbes in cover crops. And so, how much is it just you're adding more carbon, and how much is it that, you're changing something, you mentioned priming, but you're changing something about how the microbial community is working. So do you have any thoughts on kind of the role of, microbial activity or microbial communities and kind of these cover crop responses?
Yeah, that wasn't something that we looked at in our meta-analysis, just mostly due to a lack of data, looking really at the microbial community response. But I think what my guess there would be is that, we're bringing more carbon inputs into the soil. And also there's other things that are happening too, depending on the way that residue is managed. So whether we're protecting the, the topsoil from losses, and also depending on the way, again, that residue is managed, whether it's being tilled into the soil or not, and actually coming in contact with the microbial community. And so I think kind of what we kind of think is happening here, especially by bringing in especially legumes and residues that have a more favorable carbon to nitrogen ratio, is that, yeah, we're really just providing those favorable inputs the microbial community prefers for building, especially what we think of as this kind of more, mineral associated organic matter. Of course, it's quite more complex than that, right? It really depends on the soil mineralogy and whatnot, but really we're just getting more carbon into our soil, and probably providing more favorable inputs that otherwise, and again, they usually wouldn't be there for at least a good portion of the year. So that's kind of what's leading to these changes.
And do you think, because you mentioned that the timing of the cover crops, whether they're continuous or planted in the fall or over winter, what do you think is driving those seasonal differences?
Yeah, it was quite interesting, and I think the continuous was less surprising, I think, to find, but the winter kill, the fall kind of terminated cover crop was a bit more surprising, that we found that result. And I guess I would caution any kind of over interpretation of that. If you notice from those slides, it was based on a relatively few number of observations. And again, I think most of those were occurring in the southeast, so we know there's already some more favorable conditions there. So of course, there's going to be kind of some confounding across some of the factors that we looked at. But I think one of our hypotheses, especially about the autumn and winter kills, that likely there's probably a choice that producers are making about trying to get really good production before that cover crop is terminated and killed when it gets too cold. And so likely that's probably favoring legumes or other crops that really can get build up good, have either that favorable carbon to nitrogen ratio I was talking about, or just generate a lot of biomass. And so, we looked, like we said, biomass was also important as well. And so we kind of think there might be some kind of interacting things happening there. And then in terms of the continuous cover, it's probably just advantageous to always have, at least below, there's, the above and the below ground plant inputs that are going in there. And so always having some type of plant cover is really quite beneficial. And a lot of those, we observe that continuous cover, right? Not necessarily in our annual systems, but in our perennial systems where we have living cover over the entire year. And that's just another way to kind of maximize building carbon in those spaces between rows and whatnot, between our vineyards and orchard systems.
Well, thanks, Shelby. And there's a couple, some more comments about, this seminar we really asked you to focus on the carbon effects of cover crops. But, and you touched on this, but, we know there's lots of other benefits of cover crops too that we just don't have time to go into today in terms of ecosystem services. So but no, thank you so much, Shelby. And Alejandro, I don't know if you want to join us here and turn your slides on.
Okay, I think I need to be assigned there. Thank you. And let's all right, can you see my slides now?
Yep, we can see them. So we asked Shelby to focus more on the carbon side of cover cropping, and Alejandro's expertise is in the economics of cover cropping, which is the other big question of is it worth doing? So Alejandro is going to present on net returns to cover cropping. So thank you, Alejandro. Alejandro, are you having some technical difficulties?
We can't hear you if you're speaking, Alejandro.
Sorry, we'll get Alejandro back here in a minute.
Hello,
Okay, we can hear you.
all right. Really sorry, my computer just shut down.
It's
The
okay.
most inconvenient time of all. So
Yeah.
I apologize for this inconvenience. Let's see, can you please send me the link to share my screen? Okay. So
Did somebody give it to you yet?
Yeah, he should have it.
Okay.
let's see. Can you see my slides?
No, you appear to have stopped sharing.
Oh,
Can you see my slides now?
so we see like a browser window. Okay, that's it.
There
We
they
got
are.
All right. Again, I apologize for all this trouble, but thank you very much for inviting me to discuss our findings about the net returns to cover cropping. And this is a study that, or a number of studies that were mostly focused on the Midwest. So, but for introduction purposes, let's take a look at the map of the rate of adoption of cover crops by county in 2017, according to the US Census of Agriculture. You see that across the US, not many counties have a high rate of adoption of cover crops. Those who do have a high rate of adoption are located mostly on the East Coast and primarily around Maryland and the northeastern states. In Iowa, the rate of adoption of cover crops in 2017 was 4% only. And in the other Midwestern states, at the state level, the rate of adoption was always lower than 9% until 2017. So the question is, if cover crops do have all these benefits in terms of soil carbon improvements and water quality effects, why is cover crop adoption so limited? Well, that question is particularly relevant when we look at the amount of funds that were funneled to cover croppers in order to incentivize the adoption of cover crops. And those are non-negligible amounts, and still, though the rate of adoption remains quite low. So let me give you a quick rundown of why I think the rate of adoption is so low, and I'm of course open for discussion. First of all, in crop-only Midwestern production systems, cover crops are not profitable for most farmers. Now, there's a group of farmers for which cover crops are profitable, of course. Among that group, a prevalent subgroup is those farmers who participate in cost share scheme programs, and they receive payments, cost share payments, that make the net returns less negative or somewhat positive for a small subgroup of all the participants. Now, even a smaller subgroup of farmers have mixed production systems with cows mostly, and for that small subgroup of farmers, then cover crops look like a profitable option under the right conditions. So that's a quick rundown. Let's see how I arrived at these conclusions. First, we did a number of focus groups with farmers, experienced cover croppers from Iowa, Illinois, and Minnesota, and we asked them what were their motivations to use cover crops for the first time. And as you can see, the first item here is the availability of outside resources, and then to improve soil health and to abate soil erosion. We asked the same group of experienced cover croppers what their motivations were to continue using cover crops over the years, and this group of people responded that they still care about soil erosion and soil health as the main reasons to continue using cover crops, and the availability of outside resources actually went down in the ranking because, as you know, cost share programs reduce the amount of payment through time, and the availability of outside resources actually shrinks through time for cover croppers. Now, we asked these farmers what were their perceived changes in costs and revenues, and there was no single directional answer to all these items. So, for example, in terms of the herbicide use costs, most people said would expect a reduction in that line item, but some people experienced an increase. In terms of nitrogen use, we also find answers going both ways. And of course, a certain increase in costs is associated with new equipment and additional management time. In terms of perceived changes in revenues, you see farmers responded that they experienced declines in yields, some of them, and some other experienced improvements in yields. And these are cover croppers in corn-soybean rotation mostly. And then mostly increased revenues from grazing cover crops and cost share payments. So moving from asking about the opinion on changes in costs and revenues, we wanted to do something more detailed. So we adopted, or we developed with this group of farmers, a big and detailed questionnaire to evaluate partial budgets. So what are these partial budgets? This is a methodology that allows us to evaluate for each farm operator the expenses and revenues in their production system with cover crops against their expenses and revenues in their production system without cover crops. So we are asking graphically for farmers' records and opinions about the changes in revenues and costs for corn after fallow versus corn after cover crops for the same farmer and the same farm. When we asked that additional information from these focus groups, we learned that the central tendency measures indicated that on average the cost of cover crop seeds were about $20 per acre. Planting cost added an additional $20 per acre. Since most farmers were using a pre-plant burn down for the entire cornfield, using cover crops didn't require much extra herbicide cost. So that was really minor in terms of additional costs. And we allowed farmers to give us detailed information about a number of items that could change in costs between their corn following fallow and corn following cover crops. So we asked about fertility, we talked about manure, we talked about cash rent changes, soil erosion repair costs, and everything related to the potential cost savings and potential increases in costs associated with cover crops. And we learned that those, once they are measured in dollar terms, are really minor. So the subtotal for costs were about $43 per acre as additional cost. Now, once we evaluate the changes in revenue associated with cover crops, well, first of all, cost share payments averaged about $12 per acre, and that's because these were experienced cover croppers receiving a lower cost share payment than first-time cover croppers. There was an improvement in yields reported by them of about $9 per acre, and for those who had enough biomass and could save some feeding cost for their livestock, we also accounted for those cost savings, but on average, those were very, very small. So the increase in revenue from those three sources amounted to $21 on average. So the net returns comparing increases in revenue with with increases in cost results in a net revenue which is negative at about $22 per acre. And if we exclude the cost share payment received by these farmers, the net returns are even more negative at a rate of about $34 per acre. And we did have farmers who experienced positive net returns, 2 out of these 15 farmers. So we decided that that was too small of a sample size, and we conducted a regional online survey, and we had only 79 responses, mostly from Minnesota, Iowa, and Illinois, and other 8 states. And we had enough information to split the partial budgets into partial budgets for cover crops followed by corn for grain, and cover crops followed by soybeans. And these cover crops, I should say, are mostly cereal rye based mixes or single crop of cereal rye. And what we found was that on average, the extra costs across these 79 farmers were added to $35 to $37 per acre, and the average payment from cost share program amounted to $25 to $28 per acre, much higher than in our focus groups. And we found also that on average, there was a yield drag on corn phase of the rotation of about 2 bushels per acre, but on the soybean phase of the rotation, farmers experienced a yield bump of about 3 bushels per acre. So when we compare additional revenues and additional costs, we found that on average, the net returns to cover crops preceding corn were negative by $21 and positive by $25 positive for on the soybean phase. But that includes in the calculation these big cost share payments. If we exclude those cost share payments, just trying to get a grasp of how profitable the practice would be as a standalone practice, both phases of the rotation end up generating negative net returns. So that was a small sample. We decided to go to USDA NASS, hire them to conduct a representative survey of all Iowa farmers who had at least 10 acres of cover crops in 2012. based on the Census of Agriculture, and this was prior to the 2017 Census of Agriculture. So they created this stratified sample with farms of different sizes, geographical location, and rotations, farm sizes. We obtained in the end 440 responses that were very well distributed geographically and were representative of Iowa farms. And we collected information on the costs and revenues and practices that these farmers implemented in the fall of 2015 when planting cover crops, and then during the following cash crop year in 2016. And again, we followed the same logic of a partial budget. So each farmer was reporting information about the cash crop preceded by a fallow field, and the cash crop preceded by cover crop, mostly cereal rye, but not only cereal rye. So from this survey, we were able to create a number of partial budgets for cover crops followed by corn, for cover crops followed by soybeans, and also we were able to analyze factors such as termination method, cover crop mix, planting method, and so on. And the results are very robust to these different factors. What we found in summary was that seeding costs, planting costs and seed costs were the main driver of total extra costs that amounted to $34 to $35 per acre. Farmers received, the median respondent received cost share payments of about $15 to $20 per acre. For the median respondent, there was no yield effect, so no yield increase or decrease. And the net returns were negative for both of them, even accounting for these cost share payments. Now, we went on and analyzed that small subset of farmers who also had livestock in their production mix, and we evaluated the cost savings from raising the cover crop biomass in early spring. And for that subset of farmers, we found that the net returns to cover crops, once we accounted for those extra feed cost savings, the net returns were positive for both corn and soybeans, about $7 per acre for corn and $1 per acre for soybeans. So there was, of course, substantial variability in net returns driven by savings in animal feed, cost share payments, planting cost, and termination cost, and to a much smaller scale, yield differences. And as I said, results were robust to tillage methods, planting, and years of experience with cover crops. We received lots of criticism, for these results, stating that the results were inconvenient, there was no hard science, only opinion behind these results, and that we were missing long-term effects on soil health and land values. So what we did was to survey other states and to collect data from experimental plots, and also try to measure, we tried to measure long-term effects, but I will focus on the first two during my presentation. We can discuss the others during the Q&A session. So we went and with the University of Georgia, we did a few focus groups for cereal, rye, and other cover crops in an irrigated cotton and peanuts rotation, and we found pretty much the same variability of responses that we found in Iowa, Illinois, and Minnesota. In terms of the why, what are the benefits associated with cover crops in South Carolina? And this was in collaboration with Clemson University. We had 308 respondents, so we were able to split responses by cover crop users and people and farmers who don't have experience with cover crops or non-users. And out of this big list of benefits associated with cover crops, both users and non-users identified that the major benefit from cover crops is related to increase in soil organic matter and soil health, followed by reductions in soil erosion and reductions in soil compaction. Those are the benefits. Now, in terms of the challenges associated with using cover crops, again, for cover crop users and non-cover crop users, we found that the challenges were, the following challenges were tied in the first position. First of all, we had no measurable economic return, yield reduction in the following cash crop, cover crop seed cost, and increases overall crop production risks. Those are the major challenges reported by cover crop users. What about non-users? Well, they were focusing on the cost of planting and managing cover crops as their main concern. And we also conducted studies with experimental data in Iowa, and we accounted for different seeding rates, seeding methods, and termination date with a large group of researchers from Iowa State University. And one of the multiple objectives of this grant was to calculate the economic returns to cereal rye in particular. We had a split plot design, and we found that in 2018, going into a cash crop in 2019, the average net return to cereal rye was negative $39 per acre. And this was, so we had 3 locations in Iowa, different weather patterns, different precipitation, different soil types. And we had, of course, our check plots and the treated plots, comparing, using the partial budget to compare treated and check plots. We found a almost $40 difference between the treated and the check plots, unfortunately resulting in negative net returns for the treated plots. Of course, this does not include any cost share payments. These are just calculations from the experimental plots. And we repeated the experiment in the fall of 2019, going into corn in 2020, and the net returns in this case were even more negative for those plots planted to cereal rye in the fall. We didn't find major benefits or measurable benefits on weed management, soil health, or insect management from this report, and the variability of net returns had to do with the variability of cover crop biomass. And remember that cereal rye is still a crop, right? It can fail. Although it has also, and because of that, it has also high variability potential in terms of not only private, but social benefits, environmental benefits. So when comparing all the studies in just one chart and focusing only on the value of yield change, planting cover crop costs, and changes in other costs, we see that the net returns without cost share payments and without feed cost savings are negative across all these studies. Once we add cost share payments, then in some places, for some farmers, those calculations then return positive profits. And if we add the cost savings associated with having cows in the production mix, then it is much more likely that farmers can make a profit, annual profit from cover crops. But of course, that depends on the biomass too. But you don't have to take my word for it. We have tools online that you could use to calculate the net returns for cover crops terminated with herbicides. And not only that, but we have cover crop budgets with the possibility of grazing cover crops or not grazing cover crops in our website. And these are all published peer-reviewed papers, so I will be glad to share any of these studies with the audience. I think we are getting close to the end of the hour, and I want to be respectful of everybody's time, and I will just, I'm open for questions now.
Okay, well, thank you, Alejandro. Yeah, I think we get cut off kind of exactly on the hour. But I guess just one quick question. So it seems like, your last summary slide suggested that integrating livestock is the kind of most profitable way to have cover crops. Is that something that's, easy or hard for the producers to do?
It is very hard unless you already have livestock in your production mix. It really depends on the location, the kind of livestock, and even if you do have livestock, then the benefits really are dependent on the amount of biomass that can be generated in the fall and grazed, in the fall and spring and grazed in the early spring. So that's variable too. So I don't think that it would having or planting cover crops would justify starting a livestock operation. I think that it's the other way around. If you do have a livestock operation and you do plant corn and soybeans, then you could benefit from using cover crops in those acres to reduce overall costs and improve profitability for the whole farm.
Okay, and we'll see if we can squeeze in one more. There are a couple questions about, if there are payments for additional carbon, would that change the economics? Or, in addition, I guess, to the cost share payments that exist already?
Well, that's a great question, because if that were the case, if payments could be stacked, then of course that would generate more incentives and would make cover crops profitable for more farmers. But the key here is to know that not all carbon programs allow for stackable payments. So if you participate in one carbon program, you most likely will not be able to cash in payments from EQIP, for example.
Okay, well, we've hit past the hour now, so I just want to thank both our speakers one more time. And we invite you to join us for our next seminar in a few weeks from now. So thank you, everybody, for joining. Thank you to our speakers.
Thank you. Bye.
Bye.